So let's take a look at some examples on separable differential equations. So the first couple of problems, they just simply ask us whether the differential equation is separable. So just as a reminder, in order for it to be separable, if we have dy over dx on one side, then the other side must be able to be written as a product where one function is a function of x and one function is a function of y. Now, it could be that one of these functions is simply a constant. But if we have x's and y's both, then we must be able to factor it so that in one factor we have only x's and one factor we have only y's. Now notice that why does that make it separable? If we rearrange dy over dx equals g of x times p of y, we can get all the y stuff on one side, all of the x stuff on the other side. But if it's not able to be written in this format, we're not able to separate them. So to get the dx to the other side, we would multiply both sides by the x. And to get the p of y to the other side, we would divide both sides by p of y. So we would end up with something like this. So we would have every piece that has a y variable on one side. If it doesn't have a y variable, or if it has an x variable, it would be on the other side. And the phrase is separate and integrate. Once we separate to the y's on one side and the x's on the other, we integrate both sides to get our solution. Then if we happen to have an initial value, then we use that initial value to remove our constant. So here, we just want to know, okay, can we do that? And the answer is yes. In this particular, we could rewrite it as 3y plus 7 times 1. Our p of y, our function of y, would be the 3y plus 7. Our function of x is just a constant. So we have a y part and an x part that are different factors. So we could move the dx over, move that factor to the other side, and we would be able to separate our y's to one side, x's to the other. Let's take a look at this one. Initially, when we look at this one, we might see the exponent here and say, hey, this particular factor contains x's and y's in it. And things that are not separable, let's give you an example of something that's not separable. If we had this, since this is all in one factor, and that factor contains both x's and y's, it turns out we're not able to separate that. We're not able to get just y's on one side and just x's on the other. There's not a way we could rewrite that to make that occur. But here, since the addition is in the exponent, we can rewrite this as e to the 2x times e to the y. Remember, when we multiply with like bases, we add the exponents. So if we have exponents added, then we can rewrite it. So we can split this apart. We have a product. So let's write this as separate fractions. One fraction, let's put our x factors in. And then one factor, we can put our y, one of them put our y variables in. So since we could call that first factor g of x and that second one p of y, we could get the x's on one side, the y's on the other. We can move the dx over here. We can move the y factor over there. And we would have all the y's on one side, all the x's on the other. So since we were able to separate the x's and y's into separate factors, it does turn out that is separable. Now, after we get past recognizing if we can separate something or not, then we have to actually get into, okay, if we can separate it, now let's come up with a solution. So this one, we need to write it where it can be separated. So similar to the previous one, let's rewrite our e as e to the t times e to the 4x. Or we could call that 4 over x e to the 4x times 1 over e to the t, and that equals the so our x factors in one if it doesn't have an x in the other. So we want to get, let's see, if we're going to get rid of the dt on the left, we'd multiply both sides by dt. So our dt would end up on the right. So we would want to leave the e to the t on the right. We're going to have a d on the left, so we want to get this stuff to the left side. So we can divide both sides by that fraction. And if we divide by that fraction, that's going to be equivalent to multiplying by the reciprocal. So that would give us x e to the 4x over 4, or we could put a 1/4 out front. So we separated it. We got all of our x's on one side, all the t's on the other, and now we can see about integrating. So a couple of things out front. So let's leave the 1/4 out front of the integral, and let's write this x e to the 4x dx. On the other side, let's call that e to the negative t dt. And let's integrate the right side first. Remember that to integrate e to the u du, that integrates into e to the u plus c. So our u is going to be negative t. So du would be -1 dt. So we need to multiply the dt by -1 and divide by -1 out front. Or we could, if we divide by -1 out front, 1 divided by -1, that's still -1. Oops. So this is just e to the u, and that's du. So we integrate that, we get negative e to the u plus c. So that takes care of the right side. Now we need to take care of the left side. And the left side is actually something that would integrate by parts, or we can use a table to integrate this one. So I'm going to pause the video for a second and pull up the table that we can use to integrate that. So if we pull up the integration table, then remember what it looks like. Didn't mean to draw there. Let me scroll. So if we scroll down through here, starting in 81, we have ones that have an e to the u in them. So 82 is when we have a u e to the u. And that's kind of what we have here. If we had a 4 in front of the x, this would be u, and then e to the u. Well, if I put a 4 here, I would have to divide by 4 out front. Okay, well, if I do that, if I have an e to the u, then du has to correspond to u. So if u is 4x, then du would be 4 dx. So if I pick a 4 up with a dx here, I have to pick up a 4 on bottom out front also. So I have to pick up a 4 for the u, so that this is u times e to the u, and then we had to pick up a 4 with the du. So pick up 2 4s on top here, that's 4 on the bottom up front. The integral of u e to the u. And if we go back and look at the table, that integral is u minus 1 e to the u. I'm going to go ahead and substitute in. So u minus 1 e to the u. And it said plus c, but we only have to pick up the plus c on one side. All right, we're going to push it down. U minus 1 e to the u. And then in my math lab, they ask us to solve this for c. It asks us what is c equal. So we can add e to the negative t to both sides. That's 1 over 64 times 4x minus 1 e to the 4x plus e to the negative t. And that will equal some constant. Not knowing an initial value, we don't know what constant that equals. But this is an implicit solution. It has x's and t's both on the same side. All right, let's take a look at another one. So first of all, we need to see, is this separable? So we want to get dy dx by itself, so we're going to divide both sides by x squared. And then let's see if we can rewrite this. So dy dx equals, let's see if we can have one factor that's x's and one factor that's y's. So the x's, we have 3x squared minus x minus 5 on top. On bottom, we have an x squared and an x plus 1. On bottom, we have a y plus 1 factor, and we don't have any y factors on top, so we can write that as an understood 1 there. So since we have one factor that's x's, one factor that's y's, yes, this can be separated. So move the dx over on the left, dx on the right. That should be x. If we move the y's to the other side, we're going to divide by this or multiply both sides by the reciprocal. So that will give us y plus 1 on the left. And then we're leaving this on the right. Let's take a look at this one. The left side is the easy part to integrate. We just have a polynomial, so if we integrate that, we get y to the 1 bigger power over that power. If we integrate it constantly, that variable, and then we can save our plus c for the other side. Let's look at the right side. The degree on top is 2. The degree on bottom is 3. So this is not improper. So remember that if this were improper, we would have to divide it out to make it a proper fraction. But this is not improper, and it doesn't really appear to fit any of our standard formats. So if you're looking at this in homework, it gives a hint to do partial fraction decomposition. So I'm going to give us another page. I'll put a blank page here, and let's see if we can rewrite 3x squared minus x minus 5. Yeah. And let's see if we can use partial fraction decomposition to break that apart into something that is more easily integrable. So we have an x plus 1 factor on bottom. So we would want a constant on top of it. Remember, we don't need to have improper fractions in our solution. So if this is a degree of 1, we would need a degree of 0 on top. We have factors of x plus 1. We also have factors of x. And this is a repeated factor. So remember how we do that. We have to have one factor that has an x to the first and one that has an x to the second. It still can't be improper, and turns out both of those are just going to be constants. This would have to be a constant. This technically could have an x and a constant, but since that's just a higher power of this factor, it's going to be of the same degree. So this is just a constant, so that's just going to be a constant. This is just the rule when we have repeated factors. If we have the same factors of power, we need that power and each lower power till we get down to 1, a constant on top of each one of those. We need to collect take the right side, we need to put those together. In order to do so, we need the common denominator. So this first one already has an x plus 1 on bottom. It needs to pick up an x squared to have that denominator. So if we pick up an x squared on bottom, we get 1 on top. The next one has an x. We need another x on bottom, and we need an x plus 1. The next one already has an x squared on bottom, so we need an x plus 1. So now that all of those have the same denominator, x squared times x plus 1, we can put the numerators together. And for the most basic type that we did, where we had linear factors and none of them were repeated, we just simply picked values of x to satisfy and use that to find a, b, and c. That's not going to work here. So before I get ahead of myself, recall that if we have one fraction equal to one fraction and the denominators are the same, then the numerators have to be the same. So we're not just going to be plugging in values of x that will allow us to find a, b, and c. We could get one of our values that way, but we couldn't get all of them. So let's collect things that are alike. We have an ax squared, and if we were to distribute this, we would have a bx squared. So for our x squareds, we have an a, and we're going to add a b, so that we have ax squared and bx squared. Now let's look at our x's. If we distribute here, we're going to have a bx times 1, so we're going to have a b times x. And when we distribute here, we're also going to have a c times x. So if we factor that x out, we have, if we factor the x out of there, we have a b. If we factor the x out of that, we have a c. Or you could say if we combine like terms, bx plus cx is b plus c times x. We're just adding the coefficients. And then our constants, there's not going to be a constant when we distribute here, but when we distribute here, c times 1, that's a constant. So get rid of parentheses, combine like terms. This is how many x squareds we have. This is how many x's to the first, and then that's a constant. So we can relate these. A plus b has to be related to how many x squareds we have on the other side. B has to equal 3. B plus c has to be related to how many x's to the first we have on the other side. So negative 1 has to equal b plus c. And then our constant on the right and our constant on the left have to be the same. That means c is negative 5. Once we get c, we can replace c, and then that'll give us that b. If we add 5 to both sides, we'll get that b is 4. And once we know b, then we can plug that in. Subtract 4 from both sides, and we get a is negative 1. So once we know one value, plug that in, and we can get the others. So what does this mean? So when we decompose it, we're going to have a negative 1 over x. We're going to have a 4 over x. And we're going to have a negative 5 over x squared. So this integral on the right, we can break this up into 3 fractions. Negative 1 over x plus 1 and 4 over x minus 5 over x squared. Since we have three different fractions, we can integrate those separately. We could call this minus the integral of 1 over x plus 1 dx, or we could put the dx there, plus 4 times the integral, just pulling that 4 out front, of 1 over x, or we could call that dx over x. And then we can pull the 5 out front, call that dx over x squared. So this is just du over u. This is the derivative of that. So du over u integrates into natural log absolute value of u. Same thing here. Du over u integrates into natural log absolute value of u. For the last one, we can rewrite this. This is not du over u. If we take the derivative of this, it's 2x, not dx. So we could rewrite this as x to the negative 2 dx, and that's just the power rule. So we would integrate that into x to the 1 bigger power over that power, and then plus c. We get y squared over 2 plus y equals negative natural log absolute value x plus 1 plus 4 natural log absolute value of x. Two negatives will cancel, and we can call that 5x to the negative 1, or we could call that 5 over x plus c. And then I believe let's see, they give us an initial value that when x is 1, y is 1, so we can use that to find c. If x is 1, y is 1. So if we put a 1 in for y, we get plus 1 equal negative natural log, excuse me, if we put a 1 in for x, 1 plus 1 is 2, absolute value of 2 is 2, plus 4 natural log of 1. Natural log of 1 is 0, so that goes away, plus 5 times x to the negative 1, or we said we could call that 1 over x. If we put a 1 in for x, we get 1 over 1. And we can just solve that for c. So that's 5. We can subtract 5 from both sides. So we have 1 minus 5, that's negative 4, plus 1/2, which is negative 3.5 or negative 7/2. We can add natural log of 2 to both sides, and that will give us c. So that'll get c by itself. Add that to both sides, take that away from both sides. Natural log of 1 is 0. So that's c. So then we can substitute that in. Y squared over 2 plus y equals negative natural log absolute value x plus 1 plus 4 natural log absolute value of x plus 5x to the negative 1 minus 3.5 or 7/2 plus natural log 2. Substituting that in for c. All right, let's take a look at one more. We want to begin by making sure it's separable. So either negative 1, or we can call that 1 over 2. Move that to the other side, so we can multiply both sides by t. Cancel. Equals 2t times sine squared y. So yes, we have t's and y's in separate factors, so we can separate this. So we're going to get dy over sine squared y on the left. And we're going to get 2t dt on the right. And we're going to integrate both. On the right side, if we integrate, that's going to be t to the 1 bigger power over that power. So that'll give us t squared plus c. And then, remember we had rules for integrating trigonometric functions when we had sine squareds or cosine squareds on bottom. But let's look at our table to see if we can find one that looks like that. If we look through the table, we might not find something that looks exactly like this. But notice we have some that involve secant squared u's and cosecant squared u's. Well, sine, remember that 1 over sine is cosecant. So 1 over sine squared would be cosecant squared. Here is cosecant squared y dy. And we have a formula to integrate that. To integrate cosecant squared u du, we would get negative cotangent u plus c. So that's negative cotangent y. And we put our plus c on the other side. If that's u, that's the derivative of it. So u du or y dy, same difference. So that just integrates into negative cotangent. And then we were given an initial value that when x is negative 2, y is pi over 4. And that'll allow us to find c. I said x and y. We're actually t and y. So this is t and this is y. So in place of t, negative 2. In place of y, pi over 4. So negative 2 squared is 4. Cotangent of pi over 4. Remember, pi over 4 is 45 degrees, which is root 2 over 2, root 2 over 2. Cotangent is x over y, so if we do this divided by that, we're going to get 1. So that means subtract 4 from both sides. C is negative 5. So as our solution, we're going to get minus cotangent y equals t squared minus 5. And then they might ask us to solve that for t or for y, or they might take it like that.